VLSI data conversion circuits, lecture 27. So far we have seen several ways of realizing a noise transfer function. One is the so called single loop structure. The other, which we saw in the last lecture, is the cascade structure or the multi-stage noise shaping architecture called the MASH. The cascade structure, as we saw, depended on matching, because you use a second loop to digitize the error introduced by the first loop and subtract it from the output of the first loop, and this is done in the digital domain. So, one needs the transfer function of the digital cancellation filter to match the noise transfer function of the first loop, which through its inherent nature is analog. Therefore, you end up with artifacts caused by mismatch, and you may not get the order of noise shaping that you originally hoped to get, because of the leakage of the noise of the first loop into the output. Is this clear? All right. So, the next thing is to see what one has to do to implement the various building blocks of a modulator loop. So, I mean, so far we have seen the various so called system level aspects of the entire loop. We know how to derive the loop transfer function, we know what the quantizer does, and that is the A to D and the D to A, and we know that errors in the A to D thresholds do not really matter, whereas errors in the D to A thresholds can be very problematic, and so on and so forth, right. Now, the time has come to start understanding how to realize each of these building blocks in circuit form, okay, and so that we can get a or make a working delta sigma modulator, right. So, the first thing we look at is the loop filter. The loop filter, as you know, takes the output of the quantizer as one of its inputs. The input to be digitized is another of its inputs, and does some processing and is a, I mean, gives you an output sequence. Now, if the input has been already sampled, correct, then you know the filter is working off of two sequences, one is V and the other one is U. The levels are still continuous. So, this is a discrete time analog signal, right, and therefore, the filter that processes such signals is what is called a sampled data filter, right, and is often implemented using what are called switched capacitor circuits. And since the signals inside are all discrete time and analog in nature, these are what are called discrete time sigma delta modulators. Okay. So, I suppose most of you are not familiar with switch capacitor circuits. So, we will presumably come back to this mode of realizing the loop filter later on in the course, since you are doing analog IC design parallelly. Perhaps towards the end of the semester we can get back to this mode of realizing the loop filter. Another way of realizing the loop filter is to do this in continuous time, right. So, in other words, the loop filter can be realized as a continuous time structure, right, and the output of interest is not the entire waveform of the loop filter output, but only its samples. In other words, the modulator structure looks like this. All right. You understand? As far as the loop is concerned, you can fool the loop into thinking that what is there in fact here is a discrete time filter, because you are anyway sampling the output of L of S, is not it. So, as long as the samples match what you would have gotten if there was a true discrete time filter L of Z, I mean the loop would not know, so to speak, right. Now ut is not a sampled waveform, okay. U of t is continuous time. There are several advantages to doing this, as we will find out going forward, all right. And this way of realizing the loop filter results in what is called continuous time. Delta sigma modulation. Okay. So, what this L of S is trying to do therefore is to mimic the operation of a discrete time transfer function, right, where the sampled output of L of S must be the same as that would be obtained when the sequence V was pushed into a discrete time filter, right. We will get into the details a little later on, but at least now, I mean at least you intuitively you should see that this should be possible, right. How we do it is another question, but hopefully by fooling around with L of S you can make it look like some desired L of Z, all right. Now, let us refresh ourselves. Please note that V is a digital sequence, all right, and to convert it into an analog waveform you need a D to A converter. And if you go back to the very beginning of this course, right, a discrete time sequence is related, the sequence V is a discrete time sequence all right, with discrete levels also, mind you, because it is the output of an A to D converter. The sequence V here is a digital sequence with finite register length. So, these levels will be, I mean whatever, quantized, okay. Now, D to A conversion is the process, at least conceptually, of converting this into a sequence which is continuous time, but instead of discrete time impulses you have continuous time impulses. This was n, this must be t, and what is the periodicity of these samples? The sampling rate of the D to A converter. So, this is in fact of calling this, if I call this 0, 1, 2, 3, 4 and so on, I can still call this 0, 1, 2, 3, 4 and replace t with t by Ts, right. So, in principle this is what a D to A converter will do. It will take a discrete time sequence and convert it into a continuous time waveform. This is an analog waveform, right. It so turns out that its levels are quantized because the input is that way, all right. There are a couple of such a DAC is what is called an impulsive DAC, because the output is a sequence of Dirac delta functions, and if you have impulses, you know that it is most likely not practical to have such a DAC waveform. Okay. In practice, what one will do is to have a pulse shape associated with a DAC. In other words, what you do is not send out impulses proportional to the input sequence, but some multiple of a known pulse shape. Okay. So, for example, all right. Okay. So, this is what is called a non-return to 0 DAC. Everybody understands that a DAC takes an input sequence and converts it into an analog output waveform. So, the only point of contention is what the pulse shape of the DAC is. So, it can either be impulsive or can have your favorite pulse shape. Commonly used pulse shapes are the following. One is what is called the non-return to 0 DAC, where instead of putting an impulse, which we know is very difficult to generate, we have a rectangular pulse where the height of the pulse stays constant throughout the sampling period. So, such a DAC is called, in short, it is called an NRZ DAC. NRZ standing for non-return to 0, because the waveform does not return to 0. Now, given that there is a name called a non-return to 0 DAC, it must also follow that there must be something called a return to 0 DAC, where the waveform actually returns to 0 in the middle of the clock cycle. For example, this is what is called the return to 0 DAC, or in short the RZ DAC. All right. And as I said, you can choose your favorite pulse shape. NRZ and RZ DACs are commonly used pulse shapes, presumably because they are easy to generate. Right. Now, another pulse shape that one can think of is the so called exponentially decaying pulse shape. So, you have something like this, all right. Okay. So, one obvious question is, what is the difference between all these waveforms, right, or why would one want to do one versus the other? First of all, can you comment on how one can relate the spectrum of the discrete time sequence to that of this impulsive DAC output? Clearly, the output continuous time signal is a representation of the discrete time sequence. So, their spectra must be related. Given the discrete time spectrum, we should be able to determine the continuous time output spectrum. So, can somebody tell me what that relationship will be? Yes? Yeah. So, it is very straightforward. X of e to the j omega is nothing but sigma x of n e to the minus j omega n, and the x of f is nothing but sigma x of n e to the minus j 2 pi f T s times n, correct. So, as you can see, it is simply a matter of taking the spectrum of the discrete time sequence and scaling the frequency axis. Instead of omega, omega equal to 2 pi specifically becomes f equals 1 by T s or f s. Okay. So, the continuous time Fourier transform of this impulsive sequence will look like, will have images repeated at multiples of this sampling rate. Is that clear? Okay. Now, how can you relate the spectrum of this to the spectrum of the NRZ DAC output?
Instead of differentiation, it will be integral of that. Or another way is,
pass it through. If there is some sort of a filter from which you have to pass one impulse, we will get a
correct. Please note that this, once you know this spectrum, or in other words, once you know the spectrum of the impulsive DAC, finding the spectral properties of the NRZ DAC or the RZ DAC or the exponentially decaying DAC are all very straightforward. They are equivalent to taking the impulsive DAC waveform in principle, taking the impulsive DAC output and passing it through a filter whose impulse response is the DAC pulse shape, and you get the okay. So, for example, the impulsive DAC output spectrum, let us say is something like this. Okay. At multiples of Fs, you must have the spectrum repeated with the same strength, all right. That makes sense because the impulse has got the impulsive pulse has a Fourier transform which is flat, correct. Now, after passing this through an NRZ pulse shape, what is P of t for an NRZ pulse? It is 1 for 0 less than t less than Ts and 0 elsewhere, correct. So, what do you think is the Fourier transform of the, it is Ts sinc Fts. So, the sinc will have null set multiples of 1 by Ts or Fs. So, if you want to find the spectrum of the DAC whose pulse shape is an NRZ pulse, then you take this spectrum and multiply it by sinc square, and in the log scale, I mean you will have basically a nulls if you want just find the just find the Fourier transform, take this and multiply it by sinc okay. All right. For a DAC whose pulse shape is a return to 0 pulse, how will it look like? So, a return to 0 pulse shape, what is the P of t? Is if you want it to have the same DC gain as the NRZ pulse, then you must have a height of 2, but extends to only half the clock period. So, that way you will have a pulse whose DC gain is the same, right, and whose frequency response will look like all right. So, this is the RZ spectrum, this is the NRZ spectrum, and as you can see from the spectral picture, the RZ DAC spectrum has got lot more high frequency energy than the NRZ DAC spectrum, and why does that make intuitive sense? Width is less, so I mean see the amount of high frequency energy is proportional to the number of jumps you have in the, or the magnitude of the jumps you have in the waveform, correct. So, you can see that clearly in every clock sample there is a guaranteed jump, 2 jumps of equal and opposite magnitude. So, even if the input to the DAC was DC, right, the output will be a bunch of rectangular pulses. So, there will be high frequency energy, whereas if you had an NRZ DAC and the input was purely DC, the output would be free of DC, because there is a null at multiples of Fs. If the input only consisted of DC, the nulls will take care of, will remove all of the high frequency images, and you will see only a DC spectrum, and that makes sense because there will be no jumps in the time domain waveform at all if you use an NRZ DAC with a DC input. Is this clear? Okay. So, for an exponentially shaped DAC, I mean I am not going to do the math here, but it is straightforward to find the Fourier transform of the pulse shape and compute the spectrum. So, all that I want to say is that the choice of pulse shape, right, within the signal band at low frequencies, whether you choose NRZ or RZ, right, at low frequencies it does not matter. That makes sense, because on the average whether you use an NRZ DAC or an RZ DAC, the average will be the same, because one has a value of 1 for full clock period, the other one has got value 2 for half the clock period. So, on the average it is the same thing, right, but they have different high frequency properties, and you can all relate them to the spectrum of the original discrete time sequence that generated this waveform. You understand? Okay. So, as far as we are concerned, when we talk about a DAC, we need to know the sampling rate and the pulse shape, and as we discussed some time back, an ideal DAC will have, I mean, will be such that if the code here was 1 and the code here was say 2, the ratio of the 2 steps will be exactly 2, correct. But another non ideality is the fact that the steps are all not the ideal steps, there will be small differences because of mismatch, okay. And that is a non ideality, but even an ideal DAC is associated with a sampling rate and a pulse shape. The pulse shape can be either an NRZ or an RZ or an exponentially decaying pulse shape or a sinusoid shape pulse. I mean, the choice of pulse shape is yours, but you must have a pulse shape, correct. Okay. Now, we want to build a sigma delta loop, right, where we are trying to make the loop believe that the filter is discrete time. You understand? So, the question is how do we do this, all right. So, let us take an example of a first order loop as an illustration. So, let us now consider a first order discrete time delta sigma loop and see how one can use a continuous time filter to make the loop believe that it is indeed dealing with a discrete time loop filter. So, all I have done is, this is a familiar discrete time loop. As far as the loop is, as far as the loop is concerned, we want to make sure that the transfer function from E to V here is 1 minus Z inverse. So, V must be 1 minus Z inverse times E, and if the gain of the loop filter is high enough, the STF will be 1 at DC, correct. So, for the time being, let us not worry about the STF. We want to make sure, see, the feedback loop is this way, correct. So, if you want the same noise transfer, to realize the same noise transfer function with continuous time circuitry, we should focus on this whole path, that is, you break the loop here, for example, you will get the same noise transfer function if you have the same loop gain, correct. And how will you measure loop gain? In this example, I will break the loop, okay, like this, for example. Okay. I will apply an impulse here, and look at the output sequence which comes up. So, if I do that, what happens? The input sequence is an impulse, all right, and the output sequence how does it look like? Zero, 1, 1, 1, and so on. Does it make sense? All right. Now, what we want to do is to do this entire thing in continuous time, where the output of the loop filter is sampled, okay, and let me call this minus L of n, which is the actual thing that comes out, right. So, the sequence that comes out here is minus U of n minus 1. So, I am going to avoid drawing negative samples, I will simply call this minus L of n. Now, the loop filter has a transfer function Z inverse by 1 minus Z inverse. So, if you want to do this in continuous time, what is going to happen? Let us assume a DAC pulse shape. So, let us see what we need to put in the loop filter. There is clearly a sign inversion here, and we have the pulse shape of the DAC to worry about. All right. Okay. The output of the loop filter is sampled and fed back through a quantization error . Is this clear? Now, how would we break the loop? We break the loop around, we finally want the transfer function from E to V to be 1 minus Z inverse. Please note that these are all only, E is a sample sequence, V is also a sample sequence. So, we do not really care what happens in the middle, but if we break the loop here, right, and inject an impulse, we should see if this was claimed to be a, somebody claimed that this is a first order modulator. When I broke the loop here at E, apply an impulse on a discrete time impulse on one side, okay, the sequence which comes back at the other end must be exactly u of n minus 1. Is this clear? You understand? So, let us take an example of an NRZ pulse shape for the DAC. We need to talk about some pulse shape instead of leaving it as P of t. Let us call this an NRZ DAC, and to make matters simple, let us assume that the sampling rate is 1 hertz. We can always scale it to whatever we want later, all right. So, in other words, this pulse shape P of t will be 1 all the way from 0 to 1 second. What are we expecting if this loop filter is doing its job properly and mimicking a discrete time integrator properly? What sequence are we expecting here? You are expecting the output samples to look like this. Is this clear? Right. So, if I put an impulse here, so here I must inject a discrete time impulse. At the output of the DAC, what will that result in? It will result in a what? It will result in a single rectangular pulse, which is it will result in this pulse basically, correct? And the sampled output of the loop filter must look like this. You understand? So, what do you think should be there in the box? What is this? What is that level finally? 1, okay. So, what do you think must be there in the box in order that you get a waveform whose samples will be 1 when excited by a pulse as shown here? It should be n. It should be an, it could be an integrator. You understand? Okay. So, a continuous time integrator, for example, will give you if the input to the continuous time integrator was like this, the output would be, how will the output look like? How will the output look like when this is integrated? It will be a ramp at the end of 1 second, the output will be 1, after which it will be constant, and if you sample this at the sampling rate which is 1 hertz, how will it look like? The sampled output sequence looks like 0, 1, 1, 1 and so on. Okay. So, in other words, this part or rather this part here, where the input is a discrete time sequence and the output is also a discrete time sequence, is completely indistinguishable from the situation where we had a truly discrete time filter which directly processed the input sequence without having any continuous time circuit, right, which means that an integrator which is being driven by an NRZ DAC is mimicking the role of a discrete time integrator. All right, is this clear? So, since the input sequence delta of n and the output sequence coming out of the loop filter after it has gone through the loop are identical to the discrete time case, it must follow that the noise transfer function when I close a loop like this must be 1 minus Z inverse, because as far as the loop is concerned, it does not know that all this integration is being done in continuous time and is sampling the output of the continuous time filter rather than taking the samples and actually integrating them in discrete time. Is this clear? Now, the next thing is to worry about what happens to the input, correct. So, let us see that. The input is some low frequency waveform like this, right, and if the oversampling ratio is very large, this is a grossly exaggerated picture, right, where the oversampling ratio is not very large. Okay, you can see that it is kind of one cycle is occupying perhaps maybe 10 or 12 units of time. Okay. So, if you have a highly oversampled signal, the periodicity of the signal will be many samples. So, what I want to point out is that whether you have the signal like this or whether you say that it is some signal like this, all right, really does not make much of a difference, you understand. So, as far as the stepped signal approximation is concerned, you can think of it as taking u of t, sampling it with an impulse sampler, and then passing it through a filter whose pulse shape is also an NRZ pulse. Okay. This is an NRZ back pulse. This is 1 by S, this is the output. This is the quantization noise. And this is V. Rather, let me say is this clear? So, as long as the input signal is of low frequency, you can think of this as being filtered by sampling it and impulse sampling it and having an NRZ pulse shape to the input also. So, that will then allow us to represent this whole thing as what? As a 2 input discrete time integrator. There is no sampler at all here. Is this clear? So, what we have essentially done is taken a continuous time loop filter. In this case, finding what the loop filter must be turned out to be a trivial affair, right? We are able to guess. With more complicated loop filter structures, that may not be possible. So, we need to figure out a systematic way of finding the L of S, which when driven by a DAC with a known pulse shape P of t and its output is sampled at Fs, will result in the same sequence that one would have got when one used a discrete time loop filter. You understand? This kind of ad hocing will not probably work for higher order, more complicated noise transfer functions. You understand? But before we go there, we will also kind of see what happens when u of t is not really a low frequency signal. The assumption so far has been that the input to the sigma delta loop is oversampled, which means that some sampling has taken place before which means that before we sample we know that we are going to put an anti-alias filter which is going to cut off stuff at multiples of the sampling rate, right. But here no such thing is happening. This idea is just a way of understanding the equivalence between a discrete time modulator and a continuous time one, but the true modulator is only this. Okay. And here is where the, let me draw that, the true modulator is only this. A DAC with some pulse shape, this is an ADC, this is V, this is Y, this is Y of t, this is U of t, alright. So, the sampling, please notice, is happening inside the loop at the output of the loop filter. So, we have no, we have no intention of sampling before the signal enters the loop. So, one question is, do I really need to put an anti-alias filter at all? Okay. So, in other words, if this input signal which is anyway being sampled at the output of the loop filter inside consists of high frequency components along with the desired low frequency component, one question is, clearly the high frequency component cannot be represented as samples of u of t with the rectangular pulse shape, right. So, we have to wonder what will happen to this loop if the input consists not of a low frequency signal, but frequencies which can potentially alias to DC, because we have not done any anti-aliasing here. So, we would be curious to figure out what happens if the input was say a tone at frequency Fs, which in a discrete time delta sigma modulator would result in, if you did not put an anti-alias filter, a tone at Fs would alias to DC and show up in the signal band, right. If the same thing happens here, then we will say, hey, that is too bad, it is nice that we are able to realize the loop filter using continuous time circuitry, but we still need an anti-alias filter upfront to kill any signal components at multiples of the sampling rate. So, we will see what happens to this, how this loop behaves when a tone at multiples of the sampling rate is put. Okay, we will do that in the next class.